Plotting the solar eclipse path, part 1, determining the center point or the maximum eclipse. And the center point seems to be the point where the shadow of the moon is the closest to the center of the earth. So how are we going to do that? So here's the steps, the complete steps for part 1 and part 2. But today we're not going to actually plot the eclipse path. So what we need is three things. We need the eclipse date and time, and we need the eclipse node if it's ascending or descending. But this one we'll need when we start working on a globe model and show the path. So we're not going to get to this now. The use for the eclipse date, the main thing we need is the Earth's axis orientation. And here's an example. This funny looking eclipse was really posing some questions. How could it happen on the globe? And here's what I did. This is a long exposure picture with me from the left side. The left side is the sun and the moon, moving a laser pen light as if it's the shadow of the moon from west to east, and that's what we saw. So it's not impossible, it's not very hard, and the steps could be long, but it's easy, especially if you use the spreadsheet that I made specifically for that purpose. So yeah, the Earth orientation, this eclipse was during the equinox, so the sun is on the equator, and as you see, this side here is the stand or the scale of the globe model. It's on the opposite side, so these are the two equinox to the left and right. That's why we need the orientation of the Earth. The second time, the eclipse time with the date to determine the sun and moon declination angles. This is what determines the latitude of the maximum solar point, the maximum solar eclipse point. The eclipse time on its own defines the longitude of the maximum solar eclipse. So let's proceed. This is the first thing, just emphasizing that we need the date to put the globe model in the proper orientation. Now we're going to start to calculate the latitude of the moon shadow or the maximum solar eclipse point. We have some color-coded lines here. First one is the sun declination angle to the equator, and this is the sun. That's the direction of the sun. The white line is the moon declination angle, and they don't really spread that much during the solar eclipse, but just because the scale of this image is a side view of the moon and earth and the sun outside of the picture during the eclipse. The green line is the line or the shadow line of the moon, and of course it's parallel to the light source. And as you see here, this is not the moon phase from the earth, this is just to show the direction of the light. The purple line, this here, is the moon shadow spot latitude. This is the latitude here of the shadow of the moon. So this is what we need to know, this angle here from the equator to this purple line. So we'll look for some triangles in this picture, and we got a very nice triangle here. It has the distance to the moon, and it has this angle. This angle is equal to this angle, and this angle is the difference between the declination angle of the sun and the moon. So now we have this line, and I admit I'm going to be doing some bit of clumsy and crude math. It wouldn't make much difference, but I can get the accurate, very accurate by fractions of degrees, but I don't need to do that right now. So I'll just shift this line from here to here and presume that I have another triangle here, which the hypotenuse of this triangle is the radius of the Earth, and one side of it is this yellow or bluish green line. So I can get this angle through, I think, the sine equation. So this angle is the angle between the declination angle of the Sun to the shadow of the eclipse. When I get this angle, I subtract the moon declination angle from it, and so I'll have this pure angle from the center of the Earth measured from the equator until the spot or the maximum shadow point. This is how to do the latitude. Now let's go for the longitude. It's very easy. We get the time of the maximum eclipse from like time and date. Let's say if it is 1630, when the solar noon for that place, the London for example, is 1210. So the eclipse happened 4 hours and 20 minutes after the solar noon in London. That means the Earth rotated by this much. 4 hours, 0.33 multiplied by 15 degrees, and that's west, so that's 65 west. So this is the angle, and here is going to be the eclipse or the maximum solar eclipse. Now let's get to a real life example. This is the coming eclipse on July 2nd of July 2019, and as you see, this is the path of the eclipse, and right here is the maximum solar eclipse point. There it is, and we need to know the location for longitude and latitude, so I just made these lines. And for longitude, it's just around this tip here of this peninsula. I don't know what's this, California Bay or Gulf of Mexico. I'm not sure the name of this place, but that's for longitude. And for latitude, it's around between I think Peru and Chile. So the maximum solar eclipse on 1900 hours 23 minutes in that date. So we'll put these information in this beautiful site I'm going to show you here. Satellitecalculations.com, satellite SunCalc HTM, that's the site, and by default it gives some information about the sun and moon on any specific date and time. So we'll put the date and the time, the day, 2nd of July 19 hours 23. So, and right here where's the sun declination angle. So we'll put this in my spreadsheet. So we'll start filling in the spreadsheet. First thing is the date, 2nd of July 19. The time, 19:23, and the solar noon on that day. I have to go to my Sun Calc. Solar noon is 12:04. Solar noon. As you see here now, we immediately get the meridian under the solar noon, which is the maximum solar noon point or longitude line. Now for the declination angles, the sun on that specific day, on the 2nd of July 2019 at this time. Sun declination angle is 23.011. 23.011, and for the moon is 22.368. 22.368, and the moon distance is 367,463. 367 what? 463. 463. So this is the latitude. It's a minus, that means the southern hemisphere, and this in minus, this means west. So let's go and see where's that on Google Earth. Let's have a look. Let's say minus 110 and minus 18, just for simplicity. So here's minus 110. This is the longitude line, minus 110. We'll go down until it's minus 18. Minus 18. I think, yeah, it's around this point. Let's see where's minus 18 in South America. Minus 18, as you see the counter here. Here's the latitude line. Alright, so it's around the same place where I showed you. But let's put the point in a way in a circle. As you see, it's almost the same place, almost perfectly the same place as we predicted, or as it is shown on time and date. This here and this here. So now for the second part, I'll use this point and I'll orient the Earth according to the specific time. So if we are the Sun point of view, we're going to be on the Tropic of Cancer. So I'll put this tropic in the center of the screen, center of the ball, and then I'll see if this eclipse is on a descending node or ascending node. Because if it's on descending node, this means the moon is going from west to east and diving down. That's a descending node. And for ascending node, it's the opposite. It doesn't make much difference when it's displayed on a model, but just to be as accurate as possible. There's another problem with plotting the exact path on the globe model is using the method that I showed you here. Path does not include the Earth rotation, so that's another problem why I'm holding back the second part. And thank you for watching.